Hi everyone, I'm Ji. I'm a PhD student at Human-Centered Autonomy Lab at University of Illinois at Urbana-Champaign. In this video, I will speak to you about multi-modal anomaly detection for unstructured and uncertain environments, which is the work in collaboration with Distributed Autonomous Systems Lab. Let's get right to it.
Agriculture is currently facing a labor crisis. To enable the autonomous farm of the future, the field robot Terrasentia has been introduced in recent years. Terrasentia is a compact agriculture robot, which navigates through rows of crops under cluttered canopies to collect data on plant traits. Due to the low accuracy of the GPS signal under the crop canopy, either LiDAR-based or vision-based navigation algorithm has been adopted on the robot. In practice, however, due to the highly uncertain operating environment, the navigation algorithm may from time to time fail to find the correct path between the crop rows, and thus the robot may encounter various types of failures. Here are two illustrative examples. On the left, you can see the robot deviates from the center line and collides with the left row of crops, and on the right, the robot encounters weeds, which obstruct the path. So the main goal of this work is to enable the robots to identify failures automatically in highly uncertain field environments. We approach this failure identification problem using a deep supervised multi-class classifier. The model maps from a set of sensor data X to a corresponding class label Y. We assume that the sensor data is multi-modal, consisting of a high-dimensional input modality, such as LiDAR and camera stream, and a low-dimensional input modality, such as wheel encoders and IMU. The output Y of the model represents the current state of the robot. Here, 0 represents the normal case, whereas each non-zero value from 1 to C in the set corresponds to a specific type of failure. To make an inference, the high-dimensional inputs are first compressed through the feature generator, and then concatenated with other low-dimensional input as inputs to the classifier. Clearly, the classification performance of this anomaly detector heavily depends on the quality of the feature generator. The latent variables extracted by the feature generator should be distinct for different classes while preserving the high-level features of the inputs XH. For the joint training of the feature generator and the classifier, we propose the use of a supervised variational autoencoder model. This network focuses on two different but related tasks, classification and reconstruction. We will elaborate on these 2 points individually in the next few slides. As mentioned, during training, the overall loss consists of a reconstruction term and a classification term. The hyperparameter alpha here controls the relative weight between the generative and discriminative learning. Setting alpha to 0 results in a purely generative model, while setting alpha to be a large value pushes the model to be a purely discriminative model. For our application, the main goal is to find a high-quality inference model for the class label. However, we found it very useful to learn a generative model simultaneously as a regularization term. We will first focus on the classification part of the SVAE model. As you can see on the right branch of the SVAE corresponds to the discriminative model, which tries to classify the robot states correctly based on the low-dimensional inputs X, L, and the features of high-dimensional inputs generated by the encoder. For the classification part, we used a standard cross-entropy loss as the classification loss. The left branch of the SVAE corresponds to the generative model, which follows the structure of vanilla VAEs. We assume that the latent variable z follows a Gaussian distribution, whose parameters are formed by the nonlinear transformation of the original high-dimensional inputs xh through the encoder. After the sampling process, the decoder takes the latent variable z and tries to reconstruct the original data. We use the negative of the evidence lower bound in vanilla VAEs as the reconstruction loss. By virtue of the training of this generative model, the output of the encoder mu and sigma are expected to contain robust and interpretable high-level features of high-dimensional inputs. In our problem, the high-dimensional input is the LiDAR point cloud, which has a dimension of 1080, and the low-dimensional input has two parts: the readings from the wheel encoders and the handcrafted features from LiDAR. We chose these handcrafted features to be the average distances from the robot to the surrounding objects within a set of ranges of scanning angles. Concretely, we compute the average value of the LiDAR data within the following four ranges: 30 to 60 degrees, 60 to 90 degrees, 90 to 120 degrees, and 120 to 150 degrees. More generally, the input modalities of the SVAE can be extended to other sensor data and other different handcrafted features without any changes to the model architecture. During testing, we abandoned the reconstruction branch and used the classification branch as the anomaly detector. The robot state is determined by the argmax of the probability over all possible class labels. The proposed model for anomaly detection was evaluated on data collected with the Terrasentia robot in field environments from August to October 2019. We divided the operation modes during the runs into four different situations. On the top left is the normal case, where the robot navigates between crop rows without any collision. On the top right is the row collision, where the robot deviates from the center line and collide with either side of the path. On the bottom left, the robot encounters weeds which obstructed the forward path. Such untraversed obstacles typically have a larger size than the robot and is rooted in the ground, making the robot unable to traverse. On the bottom right, the robot significantly slowed down and stopped in front of a lodged plant. However, with a larger motor torque, the robot would have been able to run over such traversable obstacles. We split the dataset into a training set and a test set. Due to the rareness of the anomalous cases, such dataset is imbalanced. Therefore, we performed an undersampling of normal cases and oversampling of anomalous cases during training to fight against such imbalanced problem. We test the performance of the SVAE on the test set along with three baseline methods. The MLP is a multi-layer perceptron which maps from multi-modal input X directly to class label Y. In PCA plus MLR, the high-dimensional input XH is first compressed through principal component analysis and then concatenated with other low-dimensional input XL as the inputs to multinomial logistic regression. In VAE plus MLP, a VAE is first trained by minimizing the reconstruction loss. Then the encoder is used as a feature extractor, and the classifier is trained on the features. Note that in VAE plus MLP model, one would require a two-stage training procedure. We summarize the quantitative results in Table 1. As we can see, the SVAE model achieves the best overall performance among the four methods. With a more detailed observation, we found that the feature generator does help improve the failure identification performance. This can be seen from the fact that the MLP without a feature generator had an inferior performance compared to other three models, which all contained feature generators. Moreover, the SVAE shows a better failure identification performance than VAE plus MLP due to the joint learning of the discriminative model and the generative model. In VAE plus MLP, the latent variable z learns to be beneficial to the reconstruction task, but it is not necessarily helpful to the classification task. In the SVAE, however, the latent variable z learns to be beneficial to both tasks, and thus generates a better classification performance. Lastly, with a further analysis of the confusion matrix, we found that the PSA plus MLR confused untraversable obstacles with row collisions, as it failed to learn the global features of the LiDAR data. By contrast, we will show in the next two slides that the SVAE model manages to learn the high-level features of the LiDAR data, and thus produces better classification accuracy. As mentioned before, the SVAE in fact learns an interpretable latent space. To better visualize the physical meaning of the latent variables, we used a two-dimensional latent space. After training, we fed different combinations of Z1, Z2 to the decoder to generate the point cloud grid map on the right. As can be seen, Z1 learns to represent how wide the robot's front view is, making the point clouds in front further away as it increases. By contrast, Z2 manages to represent the orientation of the crop rows, making the point clouds orient from right to left as it increases. We also analyzed the sensitivity to the anomalies of the four models during a run. Here, the first row represents the ground truth labels, and the other four rows represent the outputs of different models. As shown, our model interrupts the normal operation of the robot only when necessary. Here is a demo run of our algorithm on the test set. The video was taken by the front camera on the robot. The bar chart on the top right shows the output probability of the anomaly detector. In this work, we introduced the SVAE, which is a new family of multi-class classifier for multi-modal failure detection, which combines VAEs with discriminative models. The training of our model is a one-stage procedure. During test time, high-dimensional modalities are compressed through the encoder to the latent space, and then concatenated with other multi-modal modalities as inputs to the classifier to make an inference. The resultant classifier outperforms baseline methods in terms of the classification accuracy in failure identification tasks. We also showed that the SVAEs are capable of extracting robust and interpretable features from high-dimensional modalities. Thank you.